So now that we have a deeper understanding of what the Flory-Huggins parameter is and what the Flory-Huggins equation is, now is the time to start talking about when things will mix and when they won't mix. So what I'm showing here is that I have a system, and you can see that the system looks really mixed. And the first thing that I want to do today is plot the volume fraction of one of the components as a function of distance. So I'll plot on the x-axis the distance, and then let's plot phi of r. And I'm actually not going to say whether this is A or B because it doesn't matter. The argument would be the same no matter which you pick. So let's say that I prepare this system, and if I'm talking about phi A for this, then I could say that phi A on average would be phi 0. In other words, if I was preparing this mixture, I might say, oh, I'm going to make a 50% A, 50% B mixture. The next thing that I want to do is I want to take a slice through this system like that, and I want to see what the volume fraction is as a function of distance as I trace my way across. So if I was to do that, you can see that in this image that on average there are about as many, or there are exactly, if I make it 50%, but there are as many A particles as there are B particles, and that they're evenly mixed. They're completely mixed up randomly. Then what I will find as I trace my way across is that on average, especially if I did this many, many, many times as my system's evolving, on average I would find that everybody has a volume fraction equal to phi bar. That's going to be the average volume fraction of the species that I have. So I measure it at 1 second, and then another second later I measure it again, and I measure it again, and I measure it again, and on and on and on, and then I average them all, and I should find a straight line like this with the average composition. In fact, this average composition had better be phi 0. So I've got that, and then what? Well, then after I do that, I can start looking at what we call fluctuations. So let's go back to our system and take a look, and instead of plotting the average, let's just plot it at one instant in time. Let's plot what the volume fraction is across my system, but only at t equals 1 second. I might find that I get something like this. Of course, it goes on and on and on forever. What is that? Well, think about what's happening in your system. You have thermal energy that's equal to kBT, and all of these things are sloshing around and moving back and moving again and moving back and so on. So the volume fraction at any instant in time is not going to be constant across the system, but it's going to deviate a little bit. So it will deviate by a small amount d phi. What is that d phi? This d phi is what we call a fluctuation. It's a fluctuation in the composition. So composition fluctuation. And these happen all the time. So what this represents in terms of this graph is there's a slight enrichment of A. And that occurs just randomly. And you can see over here, there's a little bit less A. So there's less A over here. Why? Well, because there's only a certain amount of particles in the system. So if some move over in one region, you get an enrichment, then they're not where they used to be. And so there's not a depletion of A over there. And because A and B are related to each other, then if you were to plot, for example, the volume fraction of B across a system, well, if you have an enrichment of A in one region, you will have a depletion of B. And where you have a depletion of A, you will have an enrichment of B. So these are fluctuations. And the fluctuation that I have, the magnitude of this fluctuation is going to be the volume fraction at whatever position I'm at minus the average value. So I can have a positive fluctuation, I can have an enrichment of A, or I can have a negative fluctuation where A has left the region that I'm looking at. So this happens all the time. And I can have I can characterize these fluctuations. So if I plot the same kind of thing again, this will be, let's call it the average value, so phi bar. That will be the average value of the volume fraction. And then again, if I plot A, I could have a fluctuation that looks like this. So if I wanted, I could define some kind of wavelength for my fluctuation. And we already saw that this value here is the amplitude of my fluctuation. So I could have long wavelength fluctuations, or I could have short wavelength. So I should say short wavelength fluctuations. And, you know, it's not necessarily the case that it's smooth like this. I could have another thing on top, so I could have all kinds of crazy things going on. So I could have short wavelength and long wavelength fluctuations all throughout my system. So that's what we're going to talk about today, the effect of these fluctuations on what I expect in my system at equilibrium. So let's take a step back. Let's not get to composition fluctuations yet. Let's go to a really easy case of a surface that has a block on it. So let's characterize my block by, I'll draw it kind of sideways. I'm going to try to draw it sideways. Let's see. Yeah. So this is my block. And this angle, I'll call theta. So if I have a block that's standing up on its edge, then this angle theta will be 90 degrees, or pi over 2 radians. And if my block is laying on its side, then theta will be 0. So I could plot the energy of my block if I wanted. So we could plot the energy as a function of theta. And on this axis, we'll have theta. And I'm going to have something like this. Well, the lowest energy is what? Just based on what you've done in the past, just playing with a block. If it's flat like this, that's going to be the lowest energy. So here's theta equals 0. That will be the minimum of my function. And then there's going to be some kind of shape that looks like this on both sides. So this will be minus 90 degrees and plus 90 degrees. So my potential might look a little something like that. So here's where the concept of fluctuations come in. Let's say that my block is standing up. So it's standing up like this and theta is equal to 90 degrees. Let's say that there is a fluctuation in its angle. So a fluctuation in its angle would be the size of theta minus the average value of theta. Well, the average value of theta will be 90 degrees because it's standing up. So in this expression, it's 90 degrees. That's because I picked that. I said that I was going to stand my block up like that. So why would I have a fluctuation in that angle? Well, it's standing up like this and the wind blows a little bit. It starts to wiggle back and forth like that. So what happens is the wind blows. I start to wiggle back and forth. What does that mean in terms of my angle? It means that my angle wiggles back and forth like that. That's the fluctuation. I'm wiggling back and forth and back and forth. So to make a connection maybe with what I talked about above, I could plot my angle as a function of time when the wind blows. So my average angle might be 90 degrees, but when the wind blows, my block kind of shakes back and forth. So what do I see in the angle? I see a fluctuation. any angle like that. And it could be a long fluctuation. Let's say that the wind blows not too strong, but it just blows constantly, and my block might lean to the side, and then it might come back. Or let's say that there are short bursts of wind, or that it's a swirling wind or something, and then my block moves back and forth even quicker. So just like I have with the composition, I could think of a certain wavelength in the fluctuation, a certain frequency in the fluctuation. Maybe that makes more sense here since I'm talking about time, a certain frequency in my fluctuation. So that frequency will show up here. How quickly does that angle move back and forth? So what do you know about this block, or what can you think about this block in your head? Well, if the wind just blows a little bit, it'll just rattle back and forth like I've been showing and stay stood up. What if the wind blows and it's really, really, really strong? Well, you've seen it, right? If the wind's really, really strong, you'll get plunk and the block will fall down. So if you have a small fluctuation, this point on average will just stay close to 90 degrees. And you can see why it would do that, because when this happens, the energy goes up of my block temporarily, and it would be much more advantageous if the block was standing straight back up again. So if you have a fluctuation in this angle that's small, you will increase the energy of the block on either side, and then the block will spontaneously go back to 90 degrees because that's a lower energy state. Okay? So it's almost like you have a ball in a valley. It just kind of rattles around back and forth because any small rattle increases the energy, and so it'll just spontaneously go back to the lower point. So let me draw it over here. And let me say over here, this is a small fluctuation that I drew. What if I have a large fluctuation? So what would a large fluctuation be? Well, it would be the wind blowing really, really hard. So instead of my angle just changing a little bit, my angle would change a lot. The block would flop all over the place. So a large fluctuation would look more like this. So let me label these for you. This is a small fluctuation. And this is a large fluctuation. What happens if I get a large fluctuation in that angle? Well, if I get a large fluctuation, eventually the center of mass of the particle, of the block, will be beyond the base that's supporting it. And you know from physics, if the center of mass goes beyond the base that's supporting it, you will get a torque and the block will fall down. So if you have a large fluctuation here, large enough such that the angle becomes really big, then you can see that, how do I want to draw this? This distance would be the size of that fluctuation. And if that fluctuation is large enough, then eventually it will become more advantageous. You will get over that energetic barrier. It will be more advantageous for the particle to fall down flat to where its angle is 0 degrees. So what you have in this case is you have regions that are locally stable, and we'll call those metastable. And they could be stable for a large amount of time. They could be stable for a decade. But then that once in a decade storm comes by and creates a fluctuation that's large enough to slap the block flat on the table. This point here is globally stable. It's a global minimum. And so we would call this, let me make some space. We would call this stable. And then any region that's not metastable or stable, we will call unstable. So any region roughly here to here, anything like that roughly, we would call unstable. You can think about this in terms of a ball on a hill too, just as one last example. So here's my hill. And here's a ball. If you place it exactly on the top of that hill, it could stay there for a long time. It could stay there for a couple days. Until the wind blows, and then eventually the ball will go down to its lowest energy state, which is when it has the minimum amount of height. It has decreased its gravitational potential energy the most when it's done that. So you could make a similar argument here. I won't do it in any detail, but you could plot as a function of h the potential energy of the ball as a function of h, and then you would see that when h equals 0, that would be stable. At the very, very, very top of the hill, if you get everything exactly centered, this would be metastable. And anywhere else, such as on the side of the hill, would be unstable. So this is all, it's fine to think about this in terms of nice physical models, so a ball on a hill or a block standing up or something like that. But you can see the connection, especially if you look at this graph, you can see the connection between the shape of that potential energy and the behavior of the system. So if I was to draw this one last time, let's say that I'm going to plot my free energy as a function of some parameter, as a function of position, just to make it a little simple. So this is position. Then I could have a function that looks like that. And we've seen that this shape is stable with respect to fluctuations. If I prepare my system in a state like this and I get some fluctuation in x, like that, then you see that if I create that fluctuation in x, that I've increased the energy of whatever I'm talking about. I've increased the energy of my system, because here is the energy at the minimum. And if I trace, let me draw it on this side so it's clearer. If I trace this over to here, you can see that the energy has gone up. So in terms of my function, or in terms of my system and a free energy that looks like this, x0 is going to be the position that's at equilibrium, or it's the equilibrium position. So what are the requirements for this to happen? For this to happen, the derivative of that function with respect to x should be 0. Its derivative, its first derivative should be 0. Because at this point, I have a minimum in the function, and those extreme points of my function are given by the points at which the first derivative is equal to 0. The second thing is that if this is to be stable, then the second derivative with respect to x should be what? It should be positive. Because the second derivative tells me about how concave the function is, whether it's concave up or concave down. So if that second derivative is equal or is greater than 0, then my function has positive concavity. Okay, so these give me stable points. You could imagine the opposite case, where I've got a function that's shaped like that. And so if this again is x0, this is x, f of x, then if I have a fluctuation in x, and in this particular case, it actually doesn't matter how big that fluctuation is. You can see that if this is the energy before, or the value of my function before, and this is the position of whatever that coordinate is in response to that fluctuation, then I think you can see that the energy goes down. So in this case, the first derivative, especially for where I drew this, is still equal to 0. But you can see that the second derivative is less than 0, and this is leading me to an unstable situation. So we want to apply these concepts to the free energy of mixing to understand whether our system will mix or not. So we go back and we look at the change in the free energy upon mixing per lattice site, and that's given by the Flory-Huggins equation. So we've got phi A divided by NA log of phi A plus phi B divided by NB log of phi B. And now we can add in the Flory-Huggins parameter. So plus chi times phi A times 1 minus phi A. Okay, and one last time, this is the Flory-Huggins equation. So you saw in a previous video that this function takes on different shapes depending on factors such as the value of the Flory-Huggins parameter, the volume fractions, the degrees of polymerization of the components, etc. So if I plot this, I have a couple of general cases in terms of the shape of this. So if I plot this as a function of phi A, and this is delta F mix, I have a couple of options. Again, the sign of this doesn't matter so much, and you'll see in a little bit why the sign doesn't matter. But let's just make this 0 to really show the 3 separate cases that we can have. So we can have a case like this. This is 1 and 0. We could have the case where either chi is 0 or chi is less than 0. And you saw last time that we would get a shape like that. Let's call this shape number 1. Let's say that we leave everything alone and start increasing the value of chi. So we're making chi more and more positive. And if chi was negative, that means we're making it more and more towards 0. So we're increasing its value towards positive values. Then there's going to be some point where I start to develop a little bump in the function. Let's call that 2. There will be another point, if I make this big enough, that we saw last time, where the function will actually be greater than 0 in some part in the middle. And if I get really carried away and increase chi a huge amount, eventually I could get something like that. So let's call this one 4. Let's call this one 3. So we're going to analyze shapes like this and try to understand whether or not things will mix or demix at those, or for systems that have parameters that give free energy curves that look that way. So I'll tell you first of all, and then I will prove to you that this is true, that for a curve like 1, you will get mixing. For a curve like 2, or 3. Let's see. Sometimes they'll mix. It depends on volume fractions and things like that. And then finally for 4, the system will not mix ever, period. So if you want to imagine this oil and water. So you see that the shape of this curve, or these curves, they have characteristics that are in common with this graph and with that graph. And actually they have characteristics that are in common with the graph that we drew for the block that was standing up. So our goal now is to figure out whether or not things will mix. Well, okay, number 1, I think it's clear that that's stable. Let's see why. If I was to draw that system again, and plot delta F mixing, what do I expect? Well, I expect that this point will be what I get at equilibrium. And if I was to make, or if a tiny fluctuation in composition were to occur, then you can see that the free energy would increase. So that's not very favorable. If the free energy of something increases, it's unfavorable for that to occur. And so you would just as likely get another fluctuation that would return the system back to its original state. So the system does not want to increase its free energy. Although I've done this at the symmetric point here, you can show that this would be true no matter where you are. So if instead I picked a point like this, and it was subject to some fluctuation, you can show that that point would also be stable. And I'll show you that in a second. I'll show you the way to demonstrate that. Okay, so what that means is that for us to really discuss, what do I want to say here? For us to discuss when things will mix and when they won't mix, the most interesting case for us is to consider that general shape with the bump in the middle. So this, again, delta F of mixing. Okay, so let's take a look at this curve. I'm going to redraw it, and let's look at a couple of different regions. And I'm not even going to label where 0 is because I don't care. Again, the sign of this isn't telling me anything very important in general. So let's look at a couple of regions here, and I'm going to draw them out. So you see that I have a region here with positive curvature, 2 regions with positive curvature. I have a region with negative curvature. And I have 2 inflection points. So when is there going to be an inflection point for my curve? There will be an inflection point when the second derivative is equal to 0. That will be the boundary between the regions with negative curvature, which have that second derivative less than 0, and positive curvature, which have that second derivative greater than 0. So I'm going to label these points in terms of their volume fractions. I'm going to call the point at lower values of phi A, phi prime. I'm going to label this point phi double prime. I'm going to label this point phi S prime. And I'm going to label this point phi S double prime. So we can already start to see what these are. Phi prime, phi double prime will occur when the derivative of delta F of mixing with respect to phi A is equal to 0. And then phi S prime and phi S double prime will occur when that second derivative is equal to 0. So the second derivative of delta F mix with respect to phi squared is equal to 0. So these will give me the stable points. And these will give me the spinodal points. We'll come back to this. I'm going to refer to these as binodal points. Okay, so the next thing we have to do is look at what these points are and then what we expect to occur in the different regions. So our next task then is to take this free energy curve and look at the two different regions. So what I want to do is look at the first region, which is going to be the region with negative curvature. So we'll look at the region where the second derivative is less than 0. And then after that, we'll come back and look at the region where, let's just say the first derivative, well, no, where the second derivative is greater than 0. Okay, so I don't want the extreme point. I want actually the region where it's got positive curvature. So let's draw my free energy. So picture this graph right here, and I'm going to zoom in on that region. So let me draw it. We're going to need lots of space here. So on the x-axis is phi A, and on the y-axis is the free energy of mixing. And remember that that is a function of phi A. I mean, it's a function of the degree of polymerization and the chi parameter and stuff too. But right now, let's only focus on the volume fraction. So if I zoom into that graph, I'm going to get something that looks like this. So now I'm going to do the following things. The first thing I'm going to do is I'm going to prepare a solution. I'm going to pick how much A I want in my system. So I'm going to prepare a solution. Let's say mixture. I'm going to prepare a mixture with phi A equal to phi 0. So for example, I go into the lab and I'm like, okay, I'm going to take 45% A and 55% B and mix them together. So that's what I've done. Now, in terms of this graph, that will look something like this. So right here, this is going to be the mixture that I make. And so if I trace this down to the y-axis, then initially the amount of A, well, the amount of A is going to stay the same. So the amount of A that I have in my system is going to be phi 0. And then I can go over to the y-axis, and the free energy of this mixture will be F0. That's my initial free energy. Okay, so that's the first thing. And now when I prepare my system, what's going to happen? Well, I've got thermal energy, so things are sloshing around. So I can create composition fluctuations. So there will be composition fluctuations. Let's say they occur throughout the system. What's going to be the size of that fluctuation? Well, the size of that fluctuation will be the volume fraction of A. So whatever that volume fraction is locally, minus whatever the average value is throughout the system. So the average value throughout the system is phi A. Now in the graph, what does that look like? Well, what I've done is things are sloshing around, right? So in some regions, there's going to be more A than B. So in some regions, I'm going to create something that looks like this. In other words, there's going to be some phase that has an increased free energy, and it will have a composition of A in there. Let's just say equal to phi beta. These alphas and betas have nothing to do with A or B. Well, if I have an enhancement of A over here, then I must have less B where the A came from, right? So I've got an enrichment of A over here and an enrichment of B over there. If there's an enrichment of B, then there's a depletion of A. So I'm going to create another region over here. And this region will have a volume fraction of A inside equal to phi alpha. So before we go any further, I really want to stress to you that this phase that I've created has both A and B in it. And inside of the phase, inside of that region, the volume fraction of A will be equal to phi beta. The same thing's true of the other one. So this is, I'll say here, this is A rich. The same thing's happened over here. So this point here, there's still both A and B. And the volume fraction of A is equal to phi alpha. And it is A poor. There's less A in than phi 0. So if these were pure phases, if I just created an A mixture with this volume fraction, I could go over to the y-axis, and this would have a free energy of F alpha. And this phase would have a free energy of F beta. But I don't have a pure system, right? I have a system that looks like this. If I go down on the top and draw what my system looks like, I've got regions like this that have phi beta inside, and I have other regions that have phi alpha. So what I need is I have to have a combination of those two things in my system. And I want to figure out what the free energy is. So that's the next thing that we have to do, is we need a weighted average of F alpha and F beta to calculate what the free energy of my system will be in response to that composition fluctuation. So that weighted average, I'm going to call F alpha beta. That will be the free energy of the alpha and beta phases. Now, the reason that I have to take this weighted average is I only had so much A to begin with. So I need to figure out what are the relative proportions of alpha and beta. So what are little f alpha and little f beta? How much do I weight them by? So this approach that we're going to take here is called the lever rule. And it goes something like this. Initially, I've got a volume fraction of A. So initially, phi A is equal to phi 0. And that's all there is. But now if there's two phases, then phi 0 is going to be the amount that I have of the alpha phase. So FA, the fraction of the alpha phase that I have, times the volume fraction of phi A. and then plus F beta, the fraction of the system that's in the beta phase, times the volume fraction of A in the beta phase. In fact, let me even put some words to this. This is the fraction of the system in alpha. This is the fraction of the system in beta. And this is the volume fraction of A in the alpha phase. And this is the volume fraction of A in the beta phase. Okay, so this will be how I take my weighted average, sort of. I'd like to figure out what FA and FB are, because while I also have this expression for what the total volume fraction of A is, I also have that F alpha beta is going to be the fraction of the system that's in the alpha phase multiplied by the free energy of the alpha phase in its pure state, F alpha, and then the fraction of the system that's in the beta phase multiplied by the free energy of the beta phase. And you can already see what would happen. So this is the weighted average for the free energy. And this is the, I guess you could say this is the composition. So take an example. So for example, if all of the system was in the alpha phase, then what would the free energy of the system be? The free energy of the system would just be the free energy of the alpha phase. And the same thing for B, okay? So what we're trying to do is figure out what are little f alpha and little f beta so that we can figure out what the free energy of the system is. And little f beta will be 1 minus little f alpha, because the sum of those fractions has to be equal to 1. You're either in the alpha phase, you're in the beta phase, or you're in both, but that's all you can be. So how do we calculate that? Well, the way that we can calculate that is we can go back to our expression for the composition. So we can go from here down. And we can write that phi 0 is just f alpha phi alpha, plus we'll substitute in for f beta, so we'll get 1 minus f alpha times phi beta is equal to the total amount of A that I have in my system, or the volume fraction of A that I have in my system. And I can just multiply through. So this will give me f alpha phi alpha plus phi beta, and then minus f alpha phi beta. And I can group some terms together. So I'll get, and let's take phi beta to the other side. So I'll get phi 0 minus phi beta is equal to f alpha times phi alpha minus phi beta. And just divide through, and that turned out to not be so bad. So f alpha is phi 0 minus phi beta divided by phi alpha minus phi beta. Now I'm going to rewrite this a little bit differently, because phi beta was greater than phi 0, right? Look here. Phi beta is greater than phi 0, and it's greater than phi alpha. So that means that the numerator of this expression will be negative, so that will be negative. And phi beta is bigger than phi alpha, so this will be negative. So f alpha will still be positive, but I'll have a negative number in the numerator and a negative number in the denominator. So let's just write this instead as phi beta minus phi 0 divided by phi beta minus phi alpha. So what we've done here is, if we connect these two things together, we've calculated F alpha. F alpha is the size of this segment relative to the size of the whole thing. Although actually it shouldn't be written that way. The fraction of alpha is really this distance divided by the whole thing. Okay? So I should say this is really more like F alpha. It gets weird with the lever rule because it's the opposite of what you think it should be. Okay, so F alpha is going to be the size of this chunk right here relative to the length of that entire line that connects the two. The length of that tie line. Okay, so I'm going to get rid of those dotted lines because we're going to come back to that. And I'll get rid of F alpha also. Okay, so that's kind of what that means. So we can also calculate F beta if you want. So let's see. F beta would be 1 minus F alpha, so 1 minus phi beta minus phi 0 divided by phi beta minus phi alpha. So this is the same thing as if we common denominator, all that stuff. Phi beta minus phi alpha minus phi beta minus phi 0 divided by phi beta minus phi alpha. Or some of these things cancel out. That'll cancel out. That'll cancel out. And I have a minus sign here. Let me change colors. I have a minus sign here and a minus sign here. So once again, I forgot my minus sign, and this should be a plus. And this will be phi 0 minus phi alpha divided by phi beta minus phi alpha. Okay, so that's F beta. So what I've done in doing this is notice that F beta is right here and F alpha is on the other side. So if I take that weighted average will give me this point right here. In fact, I'll make it orange so we can see it a little bit better. Okay. So the free energy of the mixture will be the weighted average of, I guess I should really draw, it's the weighted average of this value and that value. They're connected by the line. The weighted average is the point that I've drawn in the middle. And so what you can see is that the free energy, let me draw that a little nicer. I'm running out of colors here. You can see hopefully the free energy has been lowered by that fluctuation. So originally I had the free energy F0 given by this point. And then I formed the phase with F alpha and F beta as their free energies in the pure state. And the weighted average has given me that point. And sorry, this is getting really crowded, but that point there would be F alpha beta. Okay, so think about what happened. Spontaneously, there was a fluctuation just because of thermal motion. What happened because of this fluctuation is I formed two phases, one rich in A, one poor in A. The free energy of that mixture of the alpha phase and the beta phase is a weighted average depending on how much of each that I have. The result of that was a free energy that was lower than what I started with. So the free energy was lowered. Because of the fluctuation. Well, damn. The free energy is lower. Why don't I just stay there? The system is always going to tend to having a lower free energy anyway. In fact, at equilibrium, it better have its lowest free energy. So that's more favorable. Cool. So you can see what's going to happen. I'll draw it schematically. in that region with negative curvature, any fluctuation that occurs will lower the free energy of my system. So initially, I start here. Spontaneously, I have a fluctuation, and I create a phase that has less A, a phase that has more A. They have a lower free energy. Well, then I can create an even bigger fluctuation from that. And so I can have a phase that's even richer in A and even poorer in A. And their free energy will be given by that weighted average. And so you can see that, again, the free energy will be lowered by that fluctuation. Well, that's even lower than what I had to begin with. So what if I have another fluctuation? Well, if I have another fluctuation where I create a phase that's even poorer in A and even poorer in B, or richer in A, then if I connect those with the tie line and calculate their weighted average, then you'll see that once again, the free energy has been lowered. So in other words, in that region with the negative curvature, any fluctuation leads to a lower free energy. Then it's going to keep going. So if I draw my entire free energy curve, that's terrible. So if I draw the entire curve that looks like this, then you can see that if I start anywhere in that region with negative curvature, I can form fluctuations that lead to phases richer in A and phases poorer in A. The free energy of each of those phases is going to be lower than what it was initially, and it's going to keep going. The system's going to keep forming more and more, I guess I should say larger and larger fluctuations until I have these two phases, where I have phi double prime and phi prime, and those were the stable points. Or the binodals, binodal points. So anything that forms in that region, so anything that forms in this region where there's negative curvature is going to form two phases, and the compositions of those phases will be phi prime and phi double prime. Right? Okay. So back to point 2, what about the regions with positive curvature? Well, we can do the same thing. We can zoom in on one of those regions. So let me draw the free energy one last time. Here's phi A, delta F mixing, and I'll zoom in on a region that has positive curvature. And just to make a connection with what we had above, that might be phi prime or phi double prime. So, will I get fluctuations in my composition if I'm at the stable point? Yes. I always get fluctuations. So let's form one and see what happens. And now that we've gone through the lever rule, we can just do this. So let's say I have a fluctuation and I create a phase that's richer in A. So I create this one here, phi beta. And then I'll have another one over here that's got less A. phi alpha. Initially, I had a free energy of F0. Well, you can already see that both the alpha and the beta phases have higher free energies than F0. So, you could kind of argue that at this point, we don't need to do anything else. But we still do, actually. So how do we find the free energy of their combined phases? We make a tie line between the 2 points. We use the lever rule and make a weighted average. And so that point will have a free energy of F alpha beta. Let me draw that. And you can see just graphically that that free energy would increase. Okay. So I still formed the phase. I mean, the free energy went up. I still formed the phase, but I still have fluctuations happening. And I can have fluctuations that further enhance the composition of the beta phase and the alpha phase. Or I can have fluctuations that drive those phases back towards phi prime. So the free energy will always increase unless those points, those two phases, go back to phi prime. So in other words, this is stable with respect to composition fluctuations. So these regions are always stable. These regions where the curvature is negative are always unstable because any fluctuation will spontaneously lower the free energy. Down here, any small fluctuation will always raise the free energy, and so those fluctuations will die out and the system will return to its stable point, which is phi prime, or on the other side, phi double prime. Okay, so let's summarize at this point because there's one last case to consider. But to summarize, and if you're looking at this for the first time, I really encourage you, go back, follow this through very carefully, look at the graphical constructions, and make sure that you can convince yourself that the free energy will increase with a fluctuation in the stable region, or the region with positive curvature, and that the free energy in the unstable region, or the region with negative curvature, will spontaneously be lowered with respect to fluctuations. Make sure you know that. That's a very important concept. So, to summarize, if the second derivative is less than 0, then composition fluctuations always lower the free energy, and you'll get what we call phase separation. Okay, so the system will not mix. On the other hand, if the second derivative is greater than 0, then small composition fluctuations are unfavorable and will die out. So you tend to get mixing in this region. There's one last region that I haven't really talked about, though. So remember, in terms of this graph, I've got a couple points. I've already identified these points are my stable points. They're the points where the system will tend to mix. It's the lowest possible free energy that my system has, and so it's favored. That region is my unstable region, where I get spontaneous demixing. And the region that I haven't really talked about is the region between the stable point and the inflection point. So the last thing that I want to do is zoom in on this region. Okay, so the last one that we'll look at is something like this. So again, we've got delta F of mixing. This axis we have phi A. And I'm going to draw the curve in its full state. So we're not going to zoom in this case. So we'll look at that kind of curve. And so this point will be one binodal. That's the other one. These points are the inflection points. And so now you see why they're important. They are the point at which the curvature changes. So they're the point where it transitions from a positive curvature to a negative curvature. Those inflection points, again, are called the spinodal points. And what I want to do is focus in on this region between the binodal and the spinodal point. So what happens if I create a fluctuation in this region? So let's say that I prepare my sample at this volume fraction. In fact, let me zoom in. So I prepare my system at this volume fraction, and what am I going to have because of thermal energy? I'm going to have composition fluctuations. So I might form another region that's rich in A, and again, another region that's rich in B. And this is why I zoomed in, because you can see that the free energy will increase in that region. And if the free energy increases, then the fluctuation dies out. And that's just like what I showed for the case of the positive curvature, right? It's a small fluctuation, it dies out, and the system will go back to where it started. Well, what if instead I make a large fluctuation? Really large. Let's do that over here so that you can see a different case. So I prepared my system at that volume fraction, and now I create a huge fluctuation. So I'm going to create a phase that's rich in A, and let's say that it just happens to have this composition of phi double prime. And then there's such a huge fluctuation that the other phase that I form is phi prime. Well, if I connect these two by a tie line, this will be the free energy of them. This will be the weighted sum of their free energy, so that will be the free energy of the system. And you can see that the free energy will decrease. So in between those stable points, I have a couple of options. One option is that there's a small fluctuation and it dies out. The other option on this side is that I had a large fluctuation. And what did it do? It lowered the free energy of my system. This is analogous to the case of a ball on a hill. So this is analogous to the case that I drew in the previous video. Where I had a ball on top of the hill. It might sit there for 10 years and be just fine. But if the wind comes by and there's just big enough of a fluctuation, then this position will shift and the ball will roll off the hill. So the same thing is applying in this case between the binodal and the spinodal point. If there's a small fluctuation, that fluctuation will die out and the system will stay mixed. If there's a very, very large fluctuation, if the system's sitting there and I come by and I smash my fist on the table and I really jostle everything up, then there could be a really large fluctuation and then the system will become unstable and demix. So to summarize, I won't put it up there. I'll put the next point down here. If you're between phi prime and phi prime spinodal, small fluctuations die out, and your system will stay mixed. If you get a large fluctuation, either just random chance, or you put energy into the system, you smash your fist on the table, you jostle your system, it has so much energy somehow that it's able to create a large fluctuation. If that happens, and you create a large fluctuation, then this will lead to a lowering of the free energy, and so it will lead to demixing. So what's another way of saying this? In regions where the curvature is less than 0, in those regions, the system's unstable because any fluctuation lowers the free energy, and any fluctuation leads to demixing because of that. So this region is unstable. If you're close to the spinodal point, or if you're close to the binodal, and you're like right at that point, the binodal points, I guess I should say, are stable. If you're like at or around the binodal point, they're pretty much stable. In this case, if you're between the binodal and the spinodal point, the system is metastable. It'll stay mixed until there's a large enough fluctuation to cause it to demix. And so our next task then is to identify where are the spinodal points and where are the binodal points. And what does this mean in terms of the phase diagram of my system? What is my material going to do as a function of temperature and as a function of composition of my polymer? So let's start this way. Let's write down the Flory-Huggins parameter just in general. So remember, we can write it as A plus B over T, where once again, A has entropic components, or A is an entropic component to the Flory-Huggins parameter, and B over T is the energetic term. So B is really talking about energetics. So we could make A negative, we could make A 0, or we could make A very small. But let's just say that it's, we could even write it like this. Let's just say that A is 0, and we could write chi as B over T. So this is just one example of what we could do with the Flory-Huggins parameter. Now what's going to happen as I increase temperature? If I look at the limit as T goes to infinity of chi, then that would be 0, right? Because as T gets bigger and bigger and bigger, B divided by T gets smaller and smaller and smaller. So this means that as T increases, chi decreases, and mixing is favored. So this is one of those systems that you're used to where you heat it up and mixing gets more and more favorable. So let's start drawing some free energy curves for this system. Let's start at low temperature and then increase the temperature higher and higher and higher. So what I want to plot for this will be delta F of mixing at different temperatures. All right, so at low temperatures, in fact, let's start here. We'll make it blue for cold. So at low temperatures, mixing is not going to be favored. So my free energy curve will look something like this. Has that kind of parabolic shape to it. And then I'm going to increase temperature a little bit. And that parabolic curve will become smaller. But the general shape is still there. And then I'll increase temperature a little bit more. Let's make it this color. And I'll have some small minima that are less than 0. And a large thing in the middle. That region, let me make it a little bit more symmetric. That region in the middle that's unstable, we sometimes call that the miscibility gap. So you see, we start to develop 2 points that are going to be the stable points. And they've moved in a little bit. Let's increase the temperature a little bit more. So now our free energy might look something like this. So everything might be less than 0, but it still has that kind of W shape to it. And if we increase the temperature a little bit more, eventually we'll have something where we just have a little bump in the middle. And then if we increase the temperature to the highest temperature that we can, we will have a curve that looks like this. So those are all of my free energy curves. And again, I'm going from low temperature to high temperature. So in terms of this drawing down here at low temperature, I have no mixing. And at high temperature, that's where my system is going to mix. Now, as an example of what our goal is, let's start drawing where our stable points are. So initially, our stable points will be at 0 and 1. What does that mean in terms of mixing? It means that I'm going to form two phases. One phase will have 100% A, and the other phase will have 100% B, just like oil and vinegar, or oil and water, right? All oil, all water. So that's what I get at the very low temperature when I have those points like that. And then what happens? Well, I increase temperature and my mixing gets a little bit better, and I have these stable points. So at equilibrium, I expect it to form two phases with those compositions. And then I increase temperature a little bit more. Well, now my stable points become these points. So I form still two phases, but now the compositions have shifted a little bit, and the compositions are approaching the middle of the system. And now my points at the higher temperature have shifted in a little bit more. And then when I get to my highest temperature, I've got just that point. So if I trace out these binodal points, or the stable points, you'll see I kind of get this. And then that. So I could go back and do the same thing with the spinodal points. And let's make those gray. And this is the first drawing that I have where I have the spinodal points, where the curvature flips from going positive to negative. And then the spinodal moves in. And the spinodal moves in. And then there's no real spinodal point anymore. Okay? It converges to being that stable point. And I could connect these spinodal points the same way. Okay, so my drawing's a little skewed. But that's how these points are changing with temperature. So what my goal might be is that I want to track where is this true. So where is the first derivative equal to 0 for all temperatures or for all values of chi. That will give me a binodal curve, which is what I've kind of sketched out as the white dashed line. And then I could also ask myself the question, where is the second derivative of delta F mixing with respect to composition equal to 0? And how does this occur as a function of temperature? So where is this equal for all temperatures or equivalently for all values of chi? Why is that equivalent? Because remember, chi is proportional to 1 over temperature. So in this case, high temperature means low chi. Okay. So let's do that first. Actually, before we do that, let me draw a phase diagram. So I want to plot on the x-axis phi A, and on the y-axis I want to plot temperature because we're more used to temperature, right? So let's draw what happens at high temperature. Let's trace out the binodal points. Where is this? Well, at high temperature, you see there's only one point. So in terms of my phase diagram, put that point there. And then if you look at the shape of the white curve, you see how it kind of forms this parabolic shape, which is tracing out where those stable points are moving in terms of composition as I lower the temperature. So if I was to trace out those points, I would kind of get something that looks like this. If I did it for all the different temperatures possible, which I could if I knew chi. So I can connect these together. And this is what I'm going to try to solve for by taking the first derivative, and this will give me my binodal curve. And remember, what it's telling me is what are the stable compositions. And then I could go back and I could trace out where those spinodal points are. And the spinodal points, if you go back to the drawing, will kind of trace out a similar shape. Okay, so let me just draw a few in here. So again, I would do this for many, many, many different temperatures. And you could see that the spinodal would look kind of like this. So this, again, would be the spinodal curve. And this is what my phase diagram would look like, except that these curves should coincide right there. Okay? So I kind of screwed up my drawing a little bit. So that's in general what my curve looks like. And then I have a point here. In fact, let me change colors. I have one point here where the binodal and spinodal curves meet. And this is going to be a critical temperature. So if I was to trace this across, that would be a critical temperature. And because of the shape of the curve, because it occurs at high temperatures and that things demix below it, I would call this an upper critical solution temperature. Or you might have seen this abbreviation before, a Ucst. Okay, so this is what we're going to solve for. So let's do it. Let's start with taking the first derivative. That's not a partial derivative. Well, I guess it could be, whatever. Let's take the derivative of delta F mix with respect to phi A. We will set it equal to 0, and we will solve to get what phi prime and phi double prime are, or we could. And so we'll start with delta F mix per lattice site, and I'm going to divide through by kBt. And so that function, if you remember, go back to your notes, this is phi A divided by NA log of phi A, and then plus phi B divided by NB log of phi B, and then plus chi phi A 1 minus phi A. Okay, so let's take the derivative of this stuff, since we can always just divide through by kBt once we're done the derivative. In other words, if we're setting this equal to 0, kBt doesn't matter. That's why I'm dividing through. So we take the derivative. Again, we've got terms that look like phi A times the log of phi A, and then 1 minus phi A times the log of 1 minus phi A. So those are just products. So first one times the derivative of the second one plus the second one times the derivative of the first one. So if we do that, we're going to get a term that looks like, in fact, let's make this easy on ourselves. Let's say that NA will be equal to NB will be equal to N. We could do this if they weren't the same, but it's going to be much easier if we make them the same. So let's just do that. So we're going to get the first derivative. So the derivative of delta F mix with respect to phi A will give me phi A divided by N. Sorry, not phi A. It'll give me log of phi A divided by N. And then plus 1 over N. This comes from the derivative of logarithm, natural logarithm, times the first term. And then we get minus the log of 1 minus phi A divided by N. And that minus sign up front comes from that minus sign. And then we get a similar looking term. So we'll get minus 1 over N. And then for the last term, we'll get plus chi times 1 minus 2 phi A. And this should be equal to 0. Okay. Again, you just expand this, obviously, and take the derivative. just so you know where all the steps are, though. Now, what could I do? Well, remember, I'm after a phase diagram, which is how these curves vary as a function of composition and temperature, or chi. So why don't we solve this equation for chi? What is chi as a function of phi to give me that curve? So I can solve that. Let's see. So I could get that chi binodal would be equal to 1 over 1 minus 2 phi a. And then in the brackets, we get everything else because, let's see, those terms cancel. We take everything to the other side and we get minus log phi a divided by n, and then plus log of 1 minus phi a divided by n. And if we wanted, we could rearrange this. It doesn't matter, but we could also write this as 1 over 2 phi a minus 1. Basically, we factor out a minus sign from the brackets, and we get log phi a over n minus log 1 minus phi a over n. So you see, by setting NA equal to NB, what we did is we basically got these terms to cancel out. If we didn't do that, we'd still have those terms hanging around. So this is chi B for binodal. You could also say this is similar to, in fact, let me change the notation. Instead of chi B, if you were to plot this, this is really kind of like chi B as a function of phi A. And again, the little b means binodal. So I challenge you, put that into Wolfram Alpha or a graphing calculator or something and plot that and see how that looks. You should get a curve that kind of looks like the phase diagram, except it might be upside down. So what if we wanted the temperature, the binodal temperature, as a function of phi A? Because if you look at the phase diagram, when I drew this, I actually drew it with temperature on the y-axis, not the chi parameter. Well, we know that in general, so this is what we're after, we know that in general, the chi parameter can be written as A plus B over the binodal temperature. And this is equal to all of this stuff up there. So we could solve this for the binodal temperature as a function of composition. And so let me check my notes, make sure I don't leave anything off. If I was to do this, I could rearrange this slightly and I would get the logarithm of phi A divided by 1 minus phi A divided by 2 phi A minus 1 times n. Sorry, this would be equal to not the binodal temperature. This would be equal to the Flory-Huggins parameter at the binodal. And that would be equal to A plus B over the binodal temperature. So I could solve for the binodal temperature from this, and the result that I obtain is that that binodal temperature, I guess as a function of phi A, would be equal to B, whatever that is, whatever I know that to be from knowing my Flory-Huggins parameter, divided by the natural log of phi A divided by 1 minus phi A divided by 2 phi A minus 1 times n minus A. All right, so I can either figure out my phase diagram based on the chi parameter, or I can figure out my phase diagram based on solving that chi parameter for our temperature. So this gives me a phase diagram in temperature. And this will give me a phase diagram in chi. Okay, so I've got those. So in terms of this graph here, this line will be T binodal as a function of phi A. That's what I've just solved for. That's how those points are moving with respect to temperature. Or what those points would be. How do I want to say this? What the binodal points are going to be at any temperature. That's what that curve is giving me. So that's what I just solved for here. Here. Okay. And now what about the spinodal lines? Well, what are those? Those are the inflection points. So I want to take the second derivative and set that equal to 0. So I'm going to look at what is the derivative, or the second derivative, I guess, of delta F mix with respect to composition. Set that equal to 0, and I'll get whatever. Well, I just took the first derivative, so I'll just take the derivative of the second, or I'll take the derivative of the first derivative to get the second derivative. So if I do that, the second derivative is going to be, well, I've got kBt out front, but again, I divided through by that. I don't really care about that. So I'm going to have 1 over, I can put the NAs back in and the NBs because I've got rid of those as constants the first time. So I get 1 over NA times phi A plus 1 over NB times 1 minus phi A minus 2 times chi, and that's equal to 0. So again, the way I got this is I took the derivative of this thing to get that. Okay, so if you're following along, pause the video, take the derivative of that, and make sure that you get what I get. And you won't. Well, I guess you would. You will. I was looking at something else. Don't mind me. I've had too much coffee. Okay, so we would like to solve this for the chi parameter of the spinodal, or to plot the chi parameter at the spinodal as a function of phi A. And so just solving for that, we'll get 1/2. And then everything that we have above, so 1 over NA phi A plus 1 over NB 1 minus phi A. So that's that. Other thing we could do, we could solve for, again, if I do it the way that I've drawn it up here, this term will give me the spinodal line in chi. Like if I was making my phase diagram with chi on the y-axis and composition on the x-axis, then that's what I would get. If I wanted to make my phase diagram in terms of temperature like I drew above, then I could solve this because the temperature, the spinodal temperature will be equal to B divided by chi S minus A, and I've already solved for chi S. So this would be B divided by 1/2, 1 over NA phi A plus 1 over NB 1 minus phi A. Okay, we got that. Minus A. So that would be TS as a function of phi A. So that will give me the spinodal temperature as a function of composition. So in other words, this will give me the spinodal line in T. So in terms of this phase diagram that I drew, this line will be the spinodal temperature as a function of phi A. So if I know A and B, and I know the degrees of polymerization of my polymer chains, at this point, I can calculate what my phase diagram should look like. And I'm going to ask you to do that. Calculate what the phase diagram is. So I drew you a phase diagram in temperature space for a Ucst system. So I had, in other words, a system that looked like this. So as a function of temperature, I wanted to see what is my system going to do. So that was my binodal line. That was my spinodal line. As long as I know my chi parameter, I can calculate this exactly now. So now, if you think about what I've done, I can calculate where my system will be unstable, where my system will be metastable, and where my system will mix for any value of temperature and chi. Think about what that is. That's pretty powerful. Now, just based on the Flory-Huggins parameter alone, I can tell you whether a polymer blend, whether a polymer solution, or whether a regular solution is likely to mix or not mix. So at this point, we have an idea of when we will be able to mix our polymers together. So again, I drew this in temperature. If I wanted, I could draw this in terms of chi. So in terms of chi, my system would look like the reverse, because remember, chi is proportional to 1 over temperature. So this would be my system if I drew it as a function of chi. And both of these systems, let's see, green. Both of these systems are Ucst systems, because both of them have this point, which is the upper critical solution temperature. And so this means mixing is favored as T increases. So at this point, I can get back to a question that was asked of me a while ago, which is, okay, well, what if, or why do you have some systems like polynipam where the chains go from coils to globules as temperature increases and things like that? Well, as you can imagine, the opposite of a Ucst system, an upper critical solution temperature system, would be a lower critical solution temperature. So it is possible, depending on what we have for our chi parameter, to have a system like this, where instead of having an upper critical solution temperature, we have a critical temperature like this, above which the system will phase separate, that we call a lower critical solution temperature. And so this is what we call an Lcst system. And especially for those of you in biomedical engineering, you may have heard Lcst systems thrown around quite a bit because people love to talk about them in terms of their potential for drug delivery applications. So in this case, mixing is promoted upon cooling. It's the opposite of a UCST system. So an example of a UCST system would be polystyrene and cyclohexane. An example of an LCST system would be polyethylene glycol, or PEG, in water, or polynipam in water. So LCST systems are really common in aqueous environments, so water plus a polymer. They exist in other systems too, but that's where they tend to show up a lot. And so that's what an LCST system looks like if I draw it as a function of temperature. And if I drew it as a function of chi instead, then an LCST system would obviously look the opposite. Okay, so both of these are examples of an LCST system. Okay, so last thing I want to talk about today is going to be, what was I going to talk about? The LCST and UCST systems. So you can think of this chi parameter, chi in general, can be written as a plus b over t. So you can think about what this parameter does with respect to temperature. So we could make a chart like this. And we could say, let's see how I want to do this. We could put A, B, T, and chi. And there's going to be 4 cases that we can look at. Let's look at the case of A and B both being positive. So if I fill in this chart, A is positive, B is positive. What happens? I increase temperature. Does chi go up or down? I hope you can see from this expression A plus B over T that chi will decrease if I do this. Right? Because this term is positive, and the more that I increase temperature, the smaller it is. So it means this value for chi will get smaller and smaller and smaller as I increase the temperature. Okay, so if chi decreases with temperature, what kind of system do we have? Chi decreases with temperature, which means that mixing is favored as I increase temperature. So this would be a UCST system. What if A was positive and B was negative? What happens? Well, I go back, I increase temperature, and let's take a look at this. If this term is negative, then as I increase temperature, that negative term is getting smaller and smaller and smaller. So chi increases. Okay? So if chi increases with temperature, let's use a different color. Chi increases with temperature, what do we get? I increase temperature, chi gets bigger. That means that mixing is not favored. So this would be a signature of an LCST system. So I can go back and I can do the last 2. A is negative, B is positive, and I increase temperature. What's going to happen? Well, if A is negative and I'm adding something positive to it, that positive term will get smaller and smaller and smaller as I increase temperature. So I'm going to find actually that in this case, chi would decrease. And if chi decreases as I increase temperature, then that's a signature of a UCST system. And then I get my final system. A is negative, B is negative. I increase temperature, it doesn't matter. Chi will be negative always. But just for kicks here, let's see what happens. Chi is negative. Well, it'll get less negative as I increase temperature. So chi will actually go up. But in this case, I will always mix. Okay, so those are the different cases that I have for chi, and that's why sometimes I get more favored mixing as I increase temperature, and other times I get less favored mixtures and complete phase separation. So that's all I want to talk about in this video. What we're going to do next time is we're going to talk about where these critical temperatures are and how they depend on the molecular weight of the species that I'm looking at mixing together. And then we're going to move on and talk about the mechanisms by which things separate. Because remember, we've got we have three real regions here. Everything out here, outside of these lines, things mix. Anything within the spinodal is unstable and will spontaneously demix. And then anything between the spinodal and the binodal curve is metastable. And will eventually demix. So we're going to talk about two different mechanisms by which the system can demix. Okay, so that's next time. Critical points and then spinodal decomposition is how unstable regions will decompose. And then nucleation and growth is how the system will demix when it's between the spinodal and the binodal curves.